Hello everyone, I am Wei Wu from Los Alamos National Laboratory. Today I'm going to present our paper, FFT-based Gradient Sparsification for the Distributed Training of Deep Neural Networks. In the distributed training of deep neural networks, gradients need to be aggregated over the network and averaged among all processes. Such operation directly impacts the overall performance of training. Usually, there are two parallelization strategies for distributed training: prime the server and ring-style or reduce. In every iteration, each worker produces gradients. In prime the server, workers send gradients to the centralized server, and the server averages all gradients and return the result back to workers. In ring-style or reduce, a ring or reduce algorithm is adopted to average gradients. Both strategies rely on the network to communicate gradients. The gradient size of current DNNs is at a scale of 100 megabytes. With increasing size of gradients, there are two challenges that exacerbate the impact of communications in the scalability and efficiency of distributed training. The first challenge is there are enormous amounts of communications during training. This table presents the gradient size per iteration of 4 widely used neural network models and the cost of transferring those gradients over different networks. If training those models in the low-profile environment, which mostly use Ethernet, it takes seconds to exchange gradients for each process. Even in the HPC environment, which uses InfiniBand, the cost is still significant compared to the computation power of modern GPUs. The rightmost column shows the cost of communication with respect to the overall cost of every iteration with InfiniBand and V100 GPU. The communication of these models take from 18% to 64% over iteration time. Since the cost of communication is huge, some people may ask, how about overlapping communication with computation? And it is a widely used technique in HPC. To answer this question, let's look at these two figures. The figures show the cost of communication and computation of AlexNet and ResNet of every iteration. AlexNet uses large convolution kernels, so there are more opportunities to overlap the convolution layer with communication. However, models like ResNet use very small convolution kernels, so there's limited chance to overlap communication with computation. Therefore, one reason such overlap cannot always work is the degree of overlapping is largely decided by the neural network models. The second reason is the degree of overlapping is also impacted by the network bandwidth, even though it is not difficult to achieve overlapping for AlexNet with InfiniBand, but when moving to Ethernet, such overlapping becomes impossible. The previous two slides introduced two communication challenges. To prove that the communications could significantly impact the scalability of distributed training of deep neural networks, we try to weak scale the regular SGD up to 32 GPUs. As seen in the figure, the scalability is very poor. Therefore, it is very important to explore how to reduce the communication cost in order to improve the training performance. The goal of this paper is to design a compression method to reduce the communication of gradients, but still maintain accuracy. It is worth to mention that since communications are not free, even after compression, it is almost impossible to achieve ideal scalability with the regular SGD algorithm. So our goal is to improve the scalability as much as possible. This figure presents the overview of our compression framework. It includes 3 components: FFT with Top-k selection, packing sparse gradients into dense format, and range-based quantizations to convert half-precision numbers into n-bit numbers to further reduce the size of gradients. The decompression steps are the same, but in reverse order. First, let me introduce the first component, FFT with Top-k selection. Before going to the details of our compression algorithm, let me explain why gradients can be compressed. These two figures show the histogram of gradients we sampled from AlexNet and ResNet during the training. There are a lot of gradients close to zero, and they may have limited contributions in updating gradients. So several Top-k-based methods have been proposed to compress gradients by removing near-zero numbers. However, as seen on the left figure, if reconstructing the gradients after Top-k selection, the result significantly deviates from the original gradients. This motivates us to sparsify gradients in the frequency domain in order to preserve the trend of the original signal even after removing the same amount of information. The right figure presents the reconstructed gradients after FFT with Top-k. It is obvious to see it preserves more information. We used half-precision QFFT to perform FFT operations. After the FFT with Top-k selection, the low-frequency gradients are set to zero. Therefore, the gradient becomes a sparse array in memory. Transferring this sparse array over the network is still very expensive. So, in this step, we will explain how to pack the sparse array into a dense array. First, we need to create a status vector to tell if an element of the sparse array is zero or not. If it is zero, then we mark corresponding location in the status vector to zero. Otherwise, we mark it to 1. Since the unpack also requires the status vector, it will be sent over the network to the receivers along with the dense array. However, since it is a bitmap, it is much smaller than the original sparse array, even though their lengths are the same. After we have the status vector, we perform the prefix sum on the vector to get a location vector, and then use the following algorithm to convert the sparse array into a dense array. The prefix sum operation we used comes from Thrust, so it delivers very good performance. Since we used half-precision and QFFT to perform the FFT operation, after the FFT, the gradients are still 16-bit, and we want to compress them more. So in this step, we explain how to convert gradients from half-precision to n-bit float. N should be at least larger than 3, because we need 1 bit for the sum, 1 bit for the exponent, and 1 bit for the mantisum. Usually, we set n to 8 to 10 according to the compression requirement. Someone may ask, why not use the existing IEEE 754 format? This figure explains the reason. The left figure is the gradients we sampled from AlexNet. If we use the IEEE 754 format, then the range of its representable number is fixed. N is larger than the range of the actual gradients. So the number outside the range of the gradients are wasted. If n is 8-bit, then there are only 255 numbers can be used, and we do not want any number to be wasted. If we use uniform quantization, the range can be adjusted to fit the gradients. However, the data distribution does not match the distribution of the gradients. The distribution of the gradients is like a Gaussian distribution, which means more numbers are close to zero, but the uniform quantization is an equal distribution, so it is not precise. In order to create a quantization method that can adjust the range like uniform quantization, and also follows the distribution of the gradients, we present a range-based quantization. Our range-based quantization utilizes offset to represent a number. Instead of doing an offset in the decimal format, we do an offset in the binary format. So any number can be considered as an offset with epsilon. The epsilon means the minimal representable positive number. The right figure gives an example of how to convert a 32-bit float into an 8-bit range-based number. M is the number of bits left for the mantissa, and in the example, we set it to 3. EPS is the epsilon, and is set to 0.125. First, we convert the EPS into binary, and cut off the rightmost 20 bits, and then we get the binary number that is p-base. We use 1 to represent the p-base, and other numbers are just an offset with the p-base. Here example. If given input 0.256, then we convert it into binary, and also cut off the rightmost 20 bits, and then do an offset with the p-base. The result is the 8-bit format of 0.256. Converting an 8-bit number back into float is similar. Different from 8-bit IEEE 754 format, we introduce a min and max to control the range of representable numbers. Given a min and max, there are 2 numbers to tune. One is M, the other is EPS. However, when n is fixed, there are not too many choices for M, since M is less than n. So, we usually set M based on our experience, and only tune EPS. We start from a heuristic EPS like 0.125 and tune it until the total number of positive and negative representable numbers are the same. Limited by time, I will not talk about the details of tuning algorithm. Please refer to the paper. Till now, I have introduced all the key components of our FFT-based compression framework. Now I'm going to theoretically analyze the performance of the compression components and the network bandwidth toward end performance. This equation tells the cost of computation, including FFT, range-based quantization, packing, and so on. The meaning of each symbol is on the right table. The cost of communication after compression is this one. In order to compensate the cost of compression and decompression, the cost of communication should be larger than the cost of communication after compression plus 2 times the cost of compression. Here we assume the cost of compression and decompression is the same. Then we can get this equation. And it tells if the users want to benefit from our compression framework on a particular machine, what is the minimum compression ratio required? These are the results of the analysis. On the left figure, assume the throughputs of FFT, range-based quantization, packing are fixed. In practical, the throughput of FFT depends on co-FFT, and the throughput of quantization depends on memory bandwidth because it is extremely parallel. So once the GPU is fixed, these throughputs are not changed. The throughput of packing depends on the implementation, and we will discuss it later on the right figure. The x-axis is the throughput of the network, and the y-axis is the compression ratio. On the left figure, we pick 2 Top-k selection implementations. The red one is faster than the blue one. As seen on the figure, if the network is Ethernet, then no matter what Top-k selection is used, a small compression ratio could reduce the overall gradients exchange and further improve the training speed. However, if the network is 56 gigabit per second InfiniBand, in order to benefit from our compression framework, we need to use the red Top-k selection implementation, and the minimal compression ratio should be around 12. The right figure is similar. In order to benefit from the compression, we need to pick the red pack implementation and use a compression ratio larger than 12. Now I'm going to theoretical analysis why our FFT-based compression approach does not impact the convergence. First, let's make an assumption. V bar is the average gradients of each iteration, and V delta bar is the average gradients after sparsification. This assumption tells V delta bar only loses a small amount of information with respect to z bar, and an update from the specified gradients is within a bounded error range of true gradient update. We will empirically prove this assumption later in the experiment. Then we have these two theorems. It is noticed that compared with the regular SGD, we have an actual theta term on the right that increased the bound. Theta is the compression ratio. Therefore, to tie the bound back to the regular SGD, we need to shrink the theta. Limited by the time, I will not present the proven of these two theorems. Please refer to the paper. The conclusion of these two theorems is a large theta can still deliver the same accuracy as SGD, but we need to reduce the theta during the training. Now I'm going to present the results of our compression framework in terms of training performance and accuracy. In order to prove that the compression framework is not limited to any specific neural network or dataset, we experiment on two widely used neural network models, AlexNet and ResNet, along with two datasets, ImageNet and Sapphire-10. Here is how to dynamically adjust the learning rate according to the epochs. And we set batch size of AlexNet to 128 and batch size of ResNet to 64. We use all-gather instead of all-reduce to exchange gradients because the current all-reduce in MPI standard does not support sparse data format, while the gradients after compression is sparse. We conduct the experiment on the Comet machine at San Diego Supercomputing Center. Each node has 4 NVIDIA P100 GPUs, and the interconnection between nodes is InfiniBand. We implement the compression algorithm on top of synchronized SGD. First, let me show the validation of the assumption presented before. We sample the average gradients of AlexNet and ResNet after each epoch, and results are shown on the figures. As seen on both figures, alpha is indeed existed, which means the error is bounded, and the assumption is valid. Now let's look at how the compression ratio could impact the convergence of the training. The left figure presents the training using AlexNet with ImageNet dataset varies by different compression ratios. The right figure showcases the training using ResNet with Sapphire-10 dataset also varies by compression ratios. As seen on the left figure, if we drop 90% of the gradients during compression, then we lose the accuracy. However, if we drop 90% of the gradients within the first 30 epochs, and after that, the gradients are not compressed, the accuracy is low at the beginning, but will recover in the end. The same phenomenon can be observed on the right figure. Even if we drop 99% of the gradients within the first 130 epochs, after that, do not drop any gradients. Finally, the training still can converge to the same accuracy as the one without sparsification. These two figures prove the theorem 3.5. A large compression ratio theta can still deliver the same accuracy as SGD if shrinking the theta during the training. After verifying the theorems of the paper, we'll start to compare our FFT-based compression approach with other state-of-the-art compression algorithms in deep learning. Here is how to set up different compression algorithms. From the last slides, we know that the dropout ratio cannot be too large, so we set it to 85% for both Top-k and FFT with Top-k. 2 bits is a reasonable number for 10 grid because using 1 bit will lose too much information. And we let QSGD to use 8 beans. The two figures show the training cost of SGD with all the compression algorithms using AlexNet with ImageNet and ResNet with Sapphire-10. The blue line is the SGD without compression. The y-axis is the top 1 accuracy. From both figures, it is obvious to see that our approach converges much faster than others while still maintaining the same accuracy as the original SGD. If we get all the numbers from the last slide, then we can create a table like this. The table tells the FFT approach achieved a similar accuracy as the original SGD, but is 2.26 times faster. The other compression algorithms can also reach the similar accuracy, but the FFT approach performs the best in terms of the training speed. Why FFT converges faster than others? We sample the gradients of ResNet every 10 epochs during the training. Top-k loses the peak for eliminating the near-zero numbers at the same compression ratio with our approach. QSGD only presents 7 clusters for using 8 bins to represent a gradient. 10-grade shows 3 major clusters. It is noted that 10-grade show 11 bars. This is due to the aggregation of specified gradients from each process. As seen in the 4 figures, the FFT demonstrates the lowest error when reconstructing gradients for after sparsification, so it is better than others. Last, I'm going to show the result of weak scalability starting from 2 nodes to 32 nodes. In the weak scalability experiment, the batch size per GPU is not changed while increasing the number of GPUs. So the overall communication is linearly increased with the increasing of the GPUs. The y-axis of the figure is the speedup corresponding to single GPU, so the higher the better. If looking at the left figure, the AlexNet produced about 250 megabytes of gradients every iteration. So without any compression, the communication becomes a bottleneck of the entire training, leading to poor scalability. The ResNet only produced 100 megabytes of gradients every iteration, so the SGD scales better even without compression, but the slope is keeping decreasing, which means the scalability becomes worse and worse when increasing GPUs. The sky blue bar is our results. As discussed before in algorithm setting, the compression ratio of our approach reaches up to 22, so we exchange much less gradients every iteration, resulting better scalability than others. However, because of the training algorithm is still SGD, which means there is synchronization between communication and the computations. The cost of the communications cannot be overlapped, so we are not able to achieve ideal scalability. In the future, our compression can be integrated with asynchronous SGD to further improve the scalability. Finally, let me conclude the paper. In this paper, we present a novel FFT-based Sparsification along with a tunable range-based quantization that retain original gradient distribution. We introduced an analytical model to guide the compression algorithm and the selection of compression ratio according to the hardware capabilities. We theoretically prove how the compression ratio theta affect the convergence and provide a solution to recover the accuracy if the theta is set too large. Last, we evaluate our compression framework with the state-of-the-art compression methodologies and showcase our approach performs better in terms of training speed and scalability.